Today we are going to be talking about graphing logarithmic functions. By the end of this video, you should be able to convert between exponential and logarithmic forms and be able to graph logarithmic functions. First, a little bit of review from Algebra 2. The inverse of an exponential function is the logarithmic function. And we have quite a few constraints. X has to be greater than 0. A, which is the base, has to be greater than 0, but not equal to 1. And then you have y equals log base A of x if and only if a to the y equals x. So that shows the relationship between logarithms and exponentials. So we're going to take a couple of these problems and just convert between logarithmic and exponential form. So you need to pay attention to where the values are in relation to the exponential and logarithmic forms. So 2 to the x equals 32. If we convert this to a log, we would have log base 2 of 32 equals x. So the thing to remember is that the base of your exponential is also the base of your logarithm. If we have log base 3 of w equals 2, and we convert this to exponential form, then we have 3 squared equals w. Lastly, we have a log that just has a whole bunch of symbols. You can still manipulate these in the same way. Log base square of circle with an x in it equals triangle would be rewritten as square to the triangle equals circle with an x in it. Let's look at some of the basic properties of logarithms. Some of these might be familiar, some of them may not. The first one, log base a of 1 is always equal to 0. And this comes from the fact if you rewrite this as an exponential, you would have a to the 0 equals 1, and anything to the 0 power will give you 1. Our next property is log base a of a equals 1. If we rewrite this in exponential form to make sure we understand where this comes from, we have a to the first power equals a. Next, we have log base a of a to the x. That is going to equal x. If you rewrite this, you have a to the x equals a to the x. Then we have a to the log base a of m, and that will equal m. If you just think about what this log part is asking, you are saying a to some power equals m, and if that's your exponent, then your exponent is that power, so you have a to that power, which is m, because that's what you just asked to figure out. Our last property is log base a of x equals log base a of y, if and only if x equals y. And that'll be very useful when we solve logarithmic equations later. Let's look at evaluating logs. When you see log base 2 of 16, I think it is helpful to think about it in terms of the exponential. So this is asking 2 to what power gives you 16? Well, 2 to the 4th power is 16, so the answer to this log is just 4. If we look at the next one, log base 3 of 1 over 27. That's asking us 3 to what power gives us 1 over 27. When you have fractions, I find it helpful to pretend that there is not a fraction for a minute. 3 to what power would give you 27? Well, that's just 3. Since we are not looking for the 3 to what power gives us 27, we actually want 1 over 27. We know that negative exponents mean that we take the reciprocal. So this power is going to be negative 3. Our last example here, we have log base 5 of square root of 5. So we're asking 5 to what power gives us the square root of 5. If you remember from algebra 2, square root is the same as the 1/2 power. So that will be 1/2. Now, we do have two different types of logs. We have common logs and natural logs. Common logs are base 10. So log base 10 of x is the same as just log of x. So log base 10 of x is the same as just log of x. If there is no base written, then the base is 10. So if we look at a couple examples here, log of 10, saying log base 10 of 10. So 10 to what power gives us 10? 1. And then we have 2 times the log of 2.5. We need our calculators for this one. So if we do 2, and we use the log button on the left here, 2.5, and that gives us, if we round to 3 decimal places, 0.796. The other type of logarithm we have is a natural log, and that is base e. Remember that e is the irrational number. If you have log base e of x, that is written natural log, which is ln of x. So if we have natural log of e, because the base is e, if we look back at our properties of logarithms, here where we have log base a of a, here we have log base e of e, so that is going to equal 1. And then we have 5 times the natural log of 3. We need our calculator for that. 5. The natural log button is on the left where it says ln. If we round to 3 decimal places, we get 5.493. Now let's take a look at some graphs. When you are graphing logarithms, it is helpful to think about the inverse function, which is the exponential function. We know that the domain of the inverse function, the log function, is going to be the range of the original function or the exponential function, and the range of the logarithmic function is going to be the domain of its inverse exponential function. As we discussed in the previous video, for an exponential function like we have here, where it's just a to the x, the domain is all real numbers and the range is 0 to infinity. So for our logarithmic function, y equals log base a of x, our domain is going to be 0 to infinity, and our range is going to be all real numbers. So let's compare the graphs of f of x equals 2 to the x and g of x equals log base 2 of x. So first, if I think about the exponential function, we know from the previous video that this has a horizontal asymptote at y equals 0. If you find it helpful to make the t-chart, you can do that. Since our h and k values are 0, we are just starting from the origin. So this is our graph of 2 to the x. If you remember from Algebra 2, inverse functions are reflected over the line y equals x, which is this diagonal line. The other way to think about it is to take the x and y values and switch them. So if I switch the x's and the y's, since we are reflecting this graph over the line y equals x, our horizontal asymptote will become a vertical asymptote. And with our new blue table here, we have these points. So here is the graph of our logarithmic function. So let's write out the characteristics for the logarithmic function log base 2 of x, which is the blue graph. Our domain is 0 to infinity. Since there is a vertical asymptote at 0, we have a parenthesis on 0. The range is all real numbers. Clearly, as you approach the vertical asymptote, the graph is going toward negative infinity. And if you look on the right side of the graph will slowly increase forever. Our x-intercept is 1, 0. We do not have a y-intercept. This graph is increasing. Our vertical asymptote is at x equals 0. Logarithmic functions do not have a horizontal asymptote. If we look at our end behavior, on the left side of the graph, as x approaches 0 from the right, g of x is approaching negative infinity. And on the right side of the graph, as x approaches positive infinity, g of x is also approaching positive infinity. Now let's look at a couple more graphs. Our general form for a logarithmic equation is very similar to what we had for an exponential equation. If there is a coefficient in front of the log, that's going to stretch the function. We have x minus h in the parenthesis, and then any number added to the end would be our k value. That should all be reviewed from Algebra 2. So, if we look here, our h value is negative 4, and our k value is 0. So our starting point is negative 4, 0. Your vertical asymptote always goes through your starting point. So your vertical asymptote for this one will be x equals negative 4. And when we go to graph this function, I think it's helpful to think about the function 3 to the x, because that would be the inverse function since we have log base 3. So if I make a little t-chart and think about 3 to the x, to find the points for log base 3 of x, I would want to switch the x and y values. So from the starting point, I would go 1/3 to the right and down 1, 1 to the right and up 0, 3 to the right and up 1. If you want to continue going, you can go 9 to the right and up 2. And that's our function. Here we have b of x equals negative log of x plus 5. Again, our starting point is going to be -5, 0, because our h value is -5 and our k value is 0. Your vertical asymptote goes through your starting point, so it's x equals -5. Here, since there's no base written, that means that this is a common log and the base is 10. So if I think about the function 10 to the x, and then switch the x and y values, so I'm going to go over 1/10, down 1, over 1, up 0, over 10, up 1. But if we notice, we have a negative out in front. This is going to flip our graph upside down. So I'm going to take these points and reflect them over the x-axis. And here's my graph. Our last example, we have c of x equals natural log of -x minus 4. Since there is no number being added or subtracted with the x, our h value is 0. This -4 off to the side is our k value. So our starting point is 0, -4. Your vertical asymptote goes through your starting point, so that's x equals 0. Since this is a natural log, our base is e, so I'm going to think about the exponential function e to the x. You'll need your calculator to figure out approximately what these decimals are equal to. 1 over e is approximately equal to 0.368, and e is approximately equal to 2.718. So if I take these points, switch my x's and y's, and go from my starting point, I have these points. Now, since there is a negative in front of the x, this means I am going to flip my graph over the y-axis. So if I flip these points, that gives me my graph.